Good evening, everyone. I think we should wait for some 3-4 minutes so that maybe some other people want to join, so that we could wait for them. Is it fine? Hello, am I audible to everyone?
Yes, sir.
Let us wait for some time so that if anyone else wants to join. Is the screen visible? Is the screen visible? Can anyone reply?
Yes, sir. Visible.
Okay. Okay, I think we should start. It's 7:05. Uh, Good evening, everyone. I am Adnan Farooq Khan. I am a PhD scholar at IIT Delhi, and I welcome you to the second problem-solving session for the course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya from IIT Roorkee. The previous problem-solving session, in this session, we first will be briefly discussing what has been taught in this week, briefly giving the overview of that so that you can brush up these concepts, and further we'll be moving towards the problem solving session. For anyone else who has joined this time, this session will be on every Tuesday from 7 to 9. Okay, like the previous problem solving session, going first I'll be going briefly through the summary what is being taught in this week. Briefly I'll be telling about the device physics, which was some part was taught in the previous week and some in this week. So I'll be giving you the brief overview of the device physics, and then I'll be moving towards the application and analysis of the switches, like what kind of the switches are there, and their characteristics, and their uses like snubbers and gate drivers, etc. And then further I'll be briefly telling about the single phase converters, which is being taught in this week towards the end, like the uncontrolled one, like diode bridge, single phase rectifiers. Coming towards this device physics, as I had told in the previous week, like this is regarding the brush up of the idea. Can you please like turn off the mic? VS King. VS King, can you please turn off your mic? So going through the device physics, like in the previous session, I had given you the idea about this device physics, and I'll be briefly telling about that. Like I had told all these electronic switches, like the fundamental material that is the silicon, and what is the fundamental, like the basic thing that we want is that is common to every switch or a device is a PN junction. Like these devices are formed of these PN junction diodes, and how we are arrive at this PN junction, like we are having a material is a silicon, like it can be doped, or like we can add an impurity to it. Like I had previously told you about this silicon, it's a fourth group element. We can dope it with a third group element or a fifth group element. If we dope or add an impurity of like a third group element, then the silicon will be called like a p type, because since the silicon is the fourth group element, it has like the 4 electrons in its valence band. When we dope it with, when we add an impurity of like a trivalent impurity of the third group, 3 electrons of this third group, they may make the bond with the Si, and 1 will be left as it is. You can take it as a we can take it like a, there is some entity like a hole which is carrying, since it is not an electron, we can say it is like an hole with a positive charge. With the positive charge that we call as the hole. And when we dope it with an pentavalent, like which has the 5 electrons in its valence band, then it's called an n-type semiconductor, which has the 1 extra electron which helps in the conduction. Here what I would like to say is, like in the p-type, what I would like to say that in the p-type, the majority carriers are these holes, because like what are getting formed is this positive charge holes, and these are the majority carriers which will carry the current, and which will help in the conduction. And in the p-type we are having an etc electron, and that helps that in n-type there is an etc charge carrier, that's an electron which has a negative charge, and that's why we call it an n-type. Electrons are the majority carriers and holes are the minority carriers. What happens when when we bring together these p and n, a junction is formed, we call it the p-n junction. As you'll be knowing, like you would have been taught by the sir, like a depletion region is formed where we have a barrier is formed, and this and the amount of doping, that is the impurity that we will add to these semiconductors, will determine the breakdown voltage of these semiconductors. That means like the junction voltage breakdown is a function of the doping or impurity level that we add into the semiconductor. When the semiconductor is lightly doped, that means we are adding a small amount of we are adding very less impurity to this PN junction diode. That means there are not much of a carriers that are available to for the conduction purpose. This can in turn reflect in turn we can say it there is a high resistivity, or the semiconductor will have a high resistance to the flow of the current, or to the flow of the charge carriers. However, if we dope this semiconductor with enough impurities, that means the charge carriers are available in abundance, as such, it will not offer that much of a resistance, resistance to the conduction process. Therefore, this doping level, this junction break also, with the lightly doped, the barrier potential formed at the PN junction will be very large, and as such, we require a higher voltage for the breakdown of that PN junction. Thus, the breakdown voltage of a PN junction is a function of a doping level. Lower the doping level, higher the breakdown voltage. Higher the voltage it can withstand. That is the breakdown, like what voltage we can apply to it before the device breaks down. But it comes at a cost of high resistivity. Low doped PN junctions will have a high on-state resistance, and vice versa. Like if we are having a highly doped if we are having a highly doped PN junction, that will be having a low breakdown voltage, but it will be having a lesser on-state resistance. And also previously I had told you about these, we are having different kinds of devices like diodes, thyristors, BJT, IGBTs, MOSFETs, and another is a Schottky diode. Like some of them are majority carrier devices and some of them are minority carrier devices. What are these? Like the majority carrier device, here it is like a MOSFET and Schottky diode. What is meant by the majority carrier device is this that means the conduction in these devices is with the help of a majority devices. Let us say we are having an NPN MOSFET, therefore here the majority carriers are the electrons and the conduction will help with electrons. And similar to that, minority carrier devices like diodes, BJT and IGBT. Here the conduction will takes place with the help of minority carriers. Like for an NPN, the conduction will be through holes. Also, one of the concepts I had briefly discussed, and what was taught by the respected professor, is like the conductivity modulation. As I had told, when we are having a lightly doped region, we are having a higher on-state resistances. So what we want in a practical switch is we want to have as low as this on-state resistance drop, so that we can minimize the losses. So the thing is done is the conductivity modulation. In this conductivity modulation, what is being done is yeah, Priya, you want to ask any question? Okay, she has left the meeting. What is done in this conductivity modulation is some minority carriers are injected into the lightly doped region. What happens with this? When we inject more minority carriers in the lightly doped region, we are increasing the this phenomenon is concerned with this minority carrier devices. Since their conduction is dependent on these minority carriers, when we inject more minority carriers in the lightly doped region, we are making available more minority carriers. That means it can therefore it offers less it conducts more and offers a less resistance to the conduction. However, there is a drawback to it. The drawback is in terms of a reduced switching speed. This means when we have introduced more minority carriers in the lightly doped region during the conduction process, what needs to be done at the time of the turn off? We need to extract these minority carriers at the time of switching off. This will take some more of a time. When it takes more of a time, there will be some current still when the device is turned off. And as such there will be some more losses in it, since the turn off time is increased by some amount. Therefore, during that portion of a time when the switch turns and turns off, there is some current as well as some voltage there, which will cause the switching losses. So these minority carrier devices are mainly used for lower switching operations, and these majority carrier devices like MOSFETs and Schottky diodes are like MOSFETs are used for high frequency operation. However, in this minority carrier devices, like we can go up to higher voltage ratings. Coming out previously also I had discussed this, this was in the coming up to this device physics, like we had seen that if we are having the different kinds of devices, like we can categorize them in different categories. Like we are having a device which has an uncontrolled turn on and turn off, that is a diode, and a device where we have a controlled turn off but an uncontrolled controlled turn on but an uncontrolled turn off. In this category we have an SCR, like a thyristor. There's also like a device we can categorize him where we can have a control turn on as well as a control turn off. In this category, like there are GTO, BJT, IGBT and MOSFETs. Also there are devices which can handle bipolar voltage, like which can withstand both positive as well as the negative voltage. In this category, like we have a SCR thyristor as well as GTO, which is the improved version of the SCR. Devices which can handle only a unipolar voltage, in that category we have a BJT, IGBT and MOSFETs. Similarly, what we want is a device which can conduct in both ways, like positive as well as the negative current, which has the bidirectional conducting capability. In that category what we have is a triac. Sorry. Now coming to the application and analysis of the switches. So as I previously told, like the basic thing what we first learn is how to get a different levels of the voltages. Like if we want to have a lower voltage from a certain DC bus, previously we had seen we can do it by a switching circuit. Like if we have a switch, we can have different kind. If we switch it for a certain period of a time, by changing the duration for which we can switch a device, we can change our output voltage. And there we had seen, like to have this we need a switch, and this switch is what we would go through it. Well, like what is an ideal switch and what should be its features, and how will we choose certain switches for different applications. Coming out to be an ideal switch, what an ideal switch should have, like previously also I had told, like what will switch, like we can turn on switch at the turn on of the time, it can conduct the current, and we can turn off switch at the time of the turn off, it should block some amount of the current, some amount of voltage. For an ideal switch, when the switch is turned on, that means when the switch is closed, it should offer zero resistance. It should offer zero resistance and should carry an infinite amount of the current. Like this is this is not practical, but what we want ideally, the characteristic of a switch, like an ideal switch, it should in the on state, it should offer a zero resistance and should carry infinite amount of the current. Why would we go for like a zero on state resistance? Because if there is some on state resistance and there is some huge current flowing, there will be some voltage drop, and there will be some loss when there is some resistance, and there is some loss when the current is flowing through it. There will be some losses associated with it, and which can which can cause a heating up of the devices. For an ideal, we want like there should be no losses in the switch. As such, when the switch turns on, that means like when the switch is closed, it should carry infinite amount of the current. Also, the on state resistance should be very less in order to have zero or negligible power loss. And when we open the switch, when the switch is off, like at the time of of, it should be able, like previously also I had told, for the switches we have a two characteristic: how much current it will carry at the time of turn on, and how much voltage it can block. For an ideal switch, what we require for an ideal switch, it should be able to block infinite amount of this voltage. Howsoever voltage we apply across it, it should be able to block it. But practically it is not possible. In a practical switch can withstand a certain amount of the voltage. Let us say like we have a 600 volt switch. So when the switch is turned off, it will be able to block this 600 up to this 600 volt voltage. And if you go beyond that 600 voltage, it will damage this that switch or that device. But for an ideal switch, what we require is like it should be able to block, like here it should be block infinite amount of the voltage. And also at the time of turn off, there should be no current flowing through it, be it leakage or any current. Like when we turn off, there is some leakage current across the PN junction diode during the reverse bias. But what what I would but for the characteristic of an ideal switch, this reverse leakage current should be 0. And also, like what is the characteristic of this ideal switch? It should be able to conduct in both directions. Like it should carry out positive current as well as the negative current. We had seen it with different devices. Like it is not possible for different devices to carry current in the both directions. Some of the devices are able to carry the current in the both directions, and some are not. Let us say diode, it is able to conduct the current only in one direction, in the positive direction. Let us say now this SCR, it is also able to conduct the current in only one direction, that is a positive direction. And if we take a triac, it is able to conduct the current in both directions, positive as well as negative. Now the other feature of this ideal switch is like it should be able to block infinite voltage on the both sides, like positive as well as the negative. As I said, like this is also not possible. Like there are certain devices which have the bipolar voltage blocking capability, like SCR, IGBT, MOSFETs, etc. And practical switches won't be able to block this infinite amount of voltage. They will be able to block this voltage only up to a certain limit for which they are rated. Let us say a switch is rated for a 500 volt, 100 volt, or a 1000 volt. They will be able to block this voltage up to that level only. If we exceed that limit, we can cause like malfunction, or that our device can get damaged. We can cause damage to our device. The other feature of this ideal switch is like it should instantly turn on and off. When the device turn off, like before turning on, it is blocking some voltage during the turn off. If you can see this picture where my arrow is currently, when the device is in turn off condition, it is blocking certain voltage, and the current through it is 0 at that moment because the switch is open. And when we want to turn on the switch, like this voltage will come down from like this device will be blocking certain voltage, and this voltage will come down to 0, and the current will and device would start conducting from 0 to rated condition. This instant at which the switch will turn on, this should be, or off, this should be instant. Like this voltage should come to 0 instantly without any delay, and this current should go to its rated value without any delay. But however, this is not possible. This is like an ideal scenario, what we want for an ideal switch. But we know like this is not possible in the practical devices. Practical devices will take some amount of time. It will take some time from for which like this voltage will come to be 0, and this current will go from 0 to the rated condition. And for that certain moment of a time, there is both voltage as well as current there in the switch. And During that instant of a time, there will be certain switching losses associated with the switch. Why we wanted instantaneous turn on and turn off? Because for an ideal switch, we don't want it to be any losses. When there is a time delay between the turn on, like from voltage going from one level to other level, and current from going 0 to rated, there is certain portion of time where where we have both voltage and current, and that means there are some power associated with it. That is this is the switching loss that is associated with the device. Also, what we want is like we should have a complete control over other thing. What we want to have for our switch is like we should have a complete control of the device. We should be able to turn it on as per our need and turn off it as per our need. Like we should have the flexibility and and control with the switch howsoever we want it, as per our need and as per our application. Like diode is an uncontrolled device. We don't have any control over its like when it will turn on or turn off. It will all depend upon the circuitry. When the positive voltage is impressed across it, like it will get turned on. If there is a negative current or a negative voltage, the device will turn off. And other thing what we want is like we should be able to like have a control over device. We should we had discussed certain devices like MOSFET, IGBTs, SCR. They need certain gate voltage or current to turn on the device. But what we want is like we should be able to turn on or turn off the device, but it should not require any power. Like there should not be any power associated with turning on and turning off. You know that this is not possible. Like whatever, there will be certain laws that will be associated with the gate driver that will come in this subsequently with turning on and turning off of the devices. All these things, like whatever are the assumptions that have been taken for this ideal switch. Ganesh, Ganesh, you want to ask something? Okay. Whatever assumptions we have taken is only for that, like we should have zero amount of the loss associated with an ideal switch. Moving forward, like we are having the certain devices like coming to this figure. We have certain devices like we were talking about, like thyristors, GTO, IGBT, MOSFET, BJTs. This here it is shown like the range for which they can operate. Like x-axis has the frequency and y-axis has the power rating. For the thyristors, because like these are the minority carrier devices, they will be able to block very high amount of the voltage. But being minority carrier devices, you can see like they are not able, they won't be good for, like they can operate at higher frequency, but they won't be good for a higher frequency operation, because there will be higher losses associated with the switching losses, which can heat up the device and may even damage the device. And coming out to be a GTO, which is an improvement over the thyristor, they have somewhat lower voltage blocking capability as compared to the thyristor, but there is an increase in the frequency range for which it can operate. Coming out towards the IGBT, what we can see with the IGBT, like it can block higher voltage than MOSFETs, but still they are not able to block as much of voltage as thyristors and GTO. But what we can see is with IGBTs, we can operate them towards a higher frequencies as compared to GTO and thyristors. These are all minority carrier devices. Coming out to be the majority carrier devices, as we had already discussed, these majority carrier devices we can operate at higher, because these are majority carrier devices. We can operate them at higher frequencies, but their voltage blocking capability is not that much. That is why, like, you can see this MOSFET is not able to like process that much more power, because we cannot have these MOSFETs for don't come for higher voltage blocking capabilities. However, we can operate at very high frequency range at around 100K or Coming out to BJTs, these are usually associated with signal level, where they are operated for lower voltage and lower frequency levels. And there are some other devices coming like SIC. They have a properties like, if you can see towards this, they will be having the voltage blocking capability. In this region, they'll be having a voltage blocking capability higher than that of MOSFET and less than that of IGBTs, but still they will be able to operate at higher frequencies. Like some other devices are coming out to be like GaN devices. Like they are rated, they can operate at very extremely high voltage, high frequencies. They're switching losses. They have a very fast reverse recovery associated with it, and they can operate at very high frequency in this region, but their voltage blocking capability as of now is very low. So depending upon these the devices that are available to us, we are having different applications where we can use these devices. Just a minute. We can use these devices. These applications are written here in terms of the higher voltage levels to the lower, like high power requirements to lower power requirements. Like we can have a different applications like HVDCs, welding machines, or we can have a, a large drives, and in this they are rated for very high megawatt level. At some there are megawatt level, some at hundreds of kilowatts, and with the high voltage of like around 15 kV, 25 kV, somewhat like that traction systems. There mainly what is been implemented are these thyristors of very high voltage blocking capability. Now there are some IGBTs also which are of very high blocking capabilities, which are being used as of now, but traditionally what are used are these thyristors, because these are having a very high voltage blocking capability, and in these systems they are operated at lower frequency ranges. Subsequently moving to like these solar plants, buses, electric cars, where we use mainly MOSFETs or IGBTs, because we are operating at very higher frequencies, where we want to like decrease the size of this converter. And besides also we are having smaller drives where this size is the main constraint. We go for very high switching frequency. There we can use SIC or GaN, where we currently use our SIC MOSFETs or GaNs. Similar is case with the power supply or adapters, which are very smaller in size and operate smaller in size, where we use these MOSFETs or IGBTs. Coming out to this, talking about these switches, like we are having these switches, like I had told you, there is some power associated with this switch, but there are a practical switch is able to block certain amount of the voltage, and is able to conduct certain amount of the current. If the voltage voltage exceeds that blocking voltage, it can damage that switch. Also, like if there is a current higher than the current rating, let us say a switch is rated for 20 amps or 40 amps of a current, and if current exceeds that value, our switch can get damaged. These are not only things that can damage our switch can also get damaged by dV by dt rate. That means like the rate of the change of this voltage, which can cause hotspots or certain thing which can cause damage to our devices. Similar is the case, as you can see, if there is a very high change in the current through this device, di by dt will be very high. This can also result in the damage. So what we want to do is, for the protection, we want to limit this dv by dt. Let us say this dv by dt, let us say when this dv by dt is very high, we know that the current that will be flowing through the capacitor. What we do for this dv by dt, we connect a snubber. Snubber can be C type or L. If we want to limit the voltage across this switch, across the switch, we use a capacitive snubber. And if we want to limit the rate of change of the current through the device, what we use a inductive type L type on this snubber in series with the switch. As we know, like the equation that determines this the current through this capacitor is IC will be equal to CdV by dVc by dt. Let us take an assumption like this voltage is changing instantly with during a very small, like zero amount of time. Like this dV by dt will be very high, and this means like an infinite amount of current will flow through the capacitor, which is not possible. As such, what it does is like the voltage across this device, which will also be across this capacitor, this cannot happen. Like capacitor cannot have this instant change in the voltage. This means like the voltage across what is impressed across the device and this capacitor will change slowly. You would have seen, if someone would have seen like the turn on and turn off of the device. Like the device does not turn on and turn off like from 0 to 10 volts. There is some LC oscillation associated with it, and at the time of the turn on or turn off there will be some very high peak going through it. What we want to do is we want to limit that dV by dt, and for that we can connect and snub a circuit across our switches for limiting this dV by high dV by dt rate. We connect a snubber, C snubber, across this. This is an ideal case where we connect this C across this switch and L across the L in series with the device to limit the dI by dt. Actually, in the practical system, we have an R and C here, so that whatever energy will be here, that will be dissipated across the R. So what this snubber circuits have, these are used for the protection for our devices, so that our device won't get damaged. They damp and control the rate of change of our voltage as well as current. As I had seen, like in this one, capacitor is connected across and inductor in series. Other thing is like for this device we had talked about the device needs to turn off at zero power, but to turn on the device, what we need? We need a certain, coming out to be this. Let us say these are there is a switch like a MOSFET. What it needs is to turn on, it needs a plus 15 volt of a gate voltage across the GS to turn on, and to turn off it needs, let us say, minus 5 volt across the GS. So we know that this here you can see these are like the gate pulses, how we want to turn on and turn off our switch. Like these are our control pulses. These we can get from our controllers, DSP, or any where we are able to get, like op amps, we are able to get these signals, and these will determine how our switches will turn on and turn off. But these are signal level voltages. They don't have that amount of voltage. Like I told you, for like a MOSFET, it requires around 15 volt of positive voltage to turn on, but these signal level voltages are up to max up to 0 to 3 volts in case of a DSP if we get these pulse, and they won't be able to drive these switches. And what we want to do, we want to amplify these signals up to a certain voltage where they are able to drive these switches. So we want to have this, let us say there is this these are the signals, and this block here is a generic gate driver. So the input to this gate drive are these pulses, these signal level pulses, and the output is GN. Like these are the voltages that we want to impress across across the switches for turn on and turn off. And VCC here, this plus VCC and minus VCC are the voltages that we want to impress across this device that we want to have across the gate source terminal in terms of a MOSFET, and with the G terminal in case of a IGBT, and so on. For so what happens is, when we give these pulses to the gate driver and apply these voltages, and we are getting the pulses at the output of it with the amplitude, for example, of a plus 15 volt and a minus 15 volt, which are required for driving a certain switch like a MOSFET. So what this gate driver does, it amplifies our signal level voltages and provides the required power that is needed to drive certain switches. Besides this, they also, like when we go in subsequently you will go in detail in this gate driver circuitry, like you will know how this gate driver ICs and ICs that are available to us help us in like isolation as well, isolation and protection as well. So this through this gate driver we would be able to control our switches. So when we want to turn on a certain device, and we want to turn off certain device. So after that, what was taught, like first I'll be talking about the single phase converters. uh, then the course went up to this single phase AC to DC converters. Sorry, just a minute. So here what was being taught is like the rectification process. What is done is, what we do is we do AC, then convert it into a DC. Here we can have a certain like a half bridge. We use a diode bridge for an uncontrolled. We can have a SCR thyristor based, where we can have a controlled turn on and turn on. If you have a MOS IGBT MOS, we can have a control turn on and turn off. So what was taught here is a single phase diode bridge, rectifier, half bridge, as well as the full bridge. So also there were certain things that were taught here is like a THD, that is a total harmonic distortion. And what we mean by this THD, what it measures is like a if we are having a certain wave like a sine wave, it measures its purity. Can you please, Dharmesh, can you please turn off your... So what it measures is like the purity of the sine wave. By purity, what means like how close it is to the fundamental. And this THD is given by this equation, where we have THD is the root of like where this is F2 square, F3 and F4. These are like certain harmonics other than the fundamental, divided by the fundamental frequency. So when there is like, we want to have as low as THD possible. Let us say we are having a very high THD. That means like the sine wave that we want, it has a very high component of second harmonic, third harmonic, fourth harmonic, because our THD values comes out to be very high. If our these harmonics like second, third, fourth and subsequent harmonics are 0, that means our THD is 0. This means our waveform is purely sine, and there are no the harmonics associated with it and this factor THD will determine how pure or how close our sine wave is towards how close our sine wave is towards the fundamental. And why this THD is an important factor. And one thing I want to like add on here, we want to have like these THD, we want to for different there are certain like harmonics that will be in the system, like it can be second, third, fifth, seventh, whatever harmonics, but there are certain limits for the system, like if you are developing a system or a hardware, and we connect it like to a grid, and there are some IEEE standards that are provided, that how much of a THD we can have in the current, and a generic kind of a THD is like it should be below 5%, but there are also certain standards that are associated with a particular harmonic, like how much of a second harmonic can be there, what is the amplitude of that second harmonic, third, fourth, and subsequent harmonics. There are certain standards that we need to meet before developing any system or any hardware. Yeah, that was what I had wanted to add on here. There are certain limits towards like each component, each harmonic associated with each harmonic, and the generic is like it should be below 5%. Now, why we want to like add on to this now, go for this THD? Why we want to study what is the essence, like if there is a current or voltage, if it has high THD, what will be its effect? Like coming out to be this, let us say we have a grid and we have a source and there is an impedance associated with the source, and there are certain loads that are connected to it. Like this is a point, it's known as a point of common coupling, common coupling where like different loads are connected to it. Let us say we are having a power electronic load, and because of it, like the source current will have a fundamental and certain harmonics associated with it. Like if we can see, like due to this harmonic, what will happen, like our grid current will be distorted, like whatever current will be flown from here, it will be distorted, and because of that, what will be the voltage here at the point of common coupling, it will be also be distorted, and this voltage is eventually fed to other loads. There may be some sensitive loads, like there may be, because of this harmonic, if we have a motor load, we can have a torque pulsations, and if you have a, like electronical sensitive loads, if we have these harmonics, they can damage those loads also. If we have like certain telecommunication or communication wires, these harmonics can interfere with them and can hamper, uh, not hamper, like it can like interact with them, and at the output of that we won't be having like it will interfere with these signals, communication signals and control signals. uh, Besides this, due to these harmonics, there will be some losses associated with this harmonics as well, which can as such, like because of these harmonics there will be more losses, and there can be heating of these heating of the line and other equipments because of these harmonics, and can definitely hamper the operation of different things. That means we want to have these harmonics under certain limits. What has been these standards are set by IEEE, and we need to follow these standards before testing or developing any hardware. We need to stringently like follow those standards. And there are like diode bridge, this is a like uncontrolled half wave rectifier, where if we like a simple basic thing is here, what I have shown is like for an RL load. If hadn't it been the RL load, if we have an R load, what would have happened is when we have a this positive voltage, it will start conducting, like at output V load will be this only the positive half. For the negative half, it will be turned off, negative half will be turned off, and the current will follow the same because it is an R load. However, if we have a RL load, so the RL for RL load, we can have this equation, like if this is Vs, we will be having some voltage drop across this resistance, and there is some voltage across this inductor VL, which we know from the equation, this inductor equation, VL is equal to LdI by dt. So what happens in RL case is when the voltage is applied, when the positive voltage applied, this diode gets forward biased and current starts conduct, which is called V by R. So the current starts to rise, and positive voltage is being impressed, and it will reach its peak value and it will start decreasing. As soon as this voltage reaches zero, what should happen is like uh, diode should turn off, because it will be reverse biased. But that is not case. What happens with RL load, because we cannot see if we know, like if VL is equal to L di by dt. If di by dt is very high, we can get a very high voltage VL that can damage our device, or that will be get impressed across the device and it can get damaged. So we know that the current through the inductor cannot be interrupted. So what happens is this inductor polarity will change, and this current whatever will flow will continue to flow, like will come to zero. And till then, like this VL voltage, this negative voltage will be impressed across the VL. Because of this RL load, like this R device VD, it should be in case of this R load, it should be on for 180 degree of conduction, like for an half cycle. But here, due to this RL load, it is able to conduct for greater than like 180 degree. And when this current will be zero, like our load voltage will come to the zero, and our diode will get reverse biased, and it will block this negative voltage, and which can be seen by this waveform. So due to this RL load, the conduction period of this diode is increased. Similarly can be seen, like our most of our loads, they are not resistive loads, and some this what can I say is like their loads will have its own inductance. For an let us take a uncontrolled full wave rectifier, where we have like four diodes. uh, when for full wave rectification, will get this kind of a waveform, where we have a 0 to 180 degree, like half wave. We know, like there's this IL, since if we know that from the load we having a RL kind of a load, this current will increase, and will come to a certain point and will have this waveform, because like the current cannot be interrupted through an inductor. And this will get reflected in this source, where we'll have this kind of a waveform. If the inductor is if the inductor value is very high, we can assume that this load current is a straight line, and this source current will have a square wave kind of a shape. And this square wave kind of a source wave will have a THD of around 48%. And like what we require is that is not under the IEEE standards, where we need to have the THD below this 5% below this 5% level. So we need to like decrease this THD level to appreciable level, for which we'll be further seeing in the course. We use a control device, how like a power factor correction is being done, how we can operate this device at how we can operate this converter at UPF. So yeah, up to this, like you could have studied in this course. What was being taught is this, like a half bridge and a full bridge rectifier. Yeah, now what we will move towards is like problem solving session. Up to this it's fine. Am I audible to everyone now? I I'm audible now? Yeah, okay. So coming towards the first question, like some of these questions are simple, and some require some explanations that I'll be going through with. Like the first question is, what is the full form of IGCT? Like this you would have read in the course. Like there are certain options that are given, like integrated gate commuter thyristors, insulated gate commuter thyristors, insulated gate commuter transistors, integrated gate common transistors. Like if anyone knows the answer, like he can text, like na message. Someone is saying like insulated gate commuted, insulated gate commuter thyristor, and some is saying insulated gate commuter transistor. So like there are a number of, like someone is telling A, someone is telling B, and someone is telling C. Like we'll go through it, like we'll want to see. So here, sorry, like I had talked about this SCR, and we have seen this SCR and this GTO, and these are like these are they have they are like their gate are driven by the current. There are current driven devices. So these are not isolated devices. So the assumption first, like someone was telling, like isolated insulated gate, like their gate is not insulated, like gate is connected, and we tend to turn on these devices through the current. These are current turn on devices. And what here what we had seen, like the first thing, that was like a diode, that was an uncontrolled device. And further moving from a diode, what we had seen is an SCR. And SCR, we had a control turn on and control turn on, but we had no, we don't had a control turn off thing. So for an SCR, but having a minority carriers, minority carrier devices, it has a large because of doping level and high doping level. It had a, like very high on state losses. It had very high RDS on R, like no on state resistance, has very high on state resistance, due to which like there was very high losses. And an improvement over this SCR was GTO. This GTO has an improved meant in terms of lower gate inductances, lower losses, and we had an integrated lower losses. But further improvement over this GTO is IGCT. Here what we have, like we have an integrated the gate with the thyristor. Like we have an integrated gate, that's why it is called integrated gate commuter thyristor. And it is the and how it looks like is the internal structure of this IGCT is given here. Like we have a AGKN, and we have a like P and B and N minus, like which is like heavily doped and lightly doped, and we have a P and N positive in positive region towards this K and this G. So this is an improvement over the GTO, and these devices have lower on-state losses. Besides this, they also have like lower gate inductances as well as integrated gate drivers with it. That's why they are called an integrated gate commuted thyristors. As such, the like the first option is correct, like integrated gate commuted thyristors. Coming up to be the towards the second question. Towards the second question, RCIGCTs are known as. The first option is symmetrical IGCT. Sorry, there is a mistake here. IGCTs can be fabricated with reverse conducting diode in the same package. B option is symmetrical IGCTs can be fabricated with reverse conducting SCR. And C option is asymmetrical IGCT can be fabricated with high leakage inductance in the same package. And D option is asymmetrical IGCTs can be fabricated with reverse conducting diode in the same package. So a lot of you have given the option D, like this is an asymmetrical IGCT and can be fabricated with reverse conducting diode in the same package. So let us go through the answer, its solution. So before coming towards this IGCT, I have told you previously, like this IGCT is an improved version of a GTO, and GTO is an improved version of we have a certain improvements over the SCR, and we are able to get where we had a gate turn off as well in the GTO, and with IGCT is like an improvement on the GTO. So these IGCTs, they are available like with or without like reverse blocking capabilities. Like if we can see a traditional SCR, like it can block the positive voltage, and it will not be able to conduct the current till a certain gate current is given to it. Like it will have a certain gate current, then only it is able to conduct. That means it is able to block this the positive voltage to a point when we give this gate current, and such it have a positive voltage blocking, and then only it will conduct this positive current. Similar to that, we know that as SCR can block this negative voltage. However, there are certain like these IGCTs which don't have this reverse blocking capability, and they can block only the forward voltage and can conduct this forward current. So coming out to be this symmetrical symmetrical IGCT. Now we have like two types of this IGCTs. We have a symmetrical and we can have a asymmetrical. And what is a symmetrical IGCT? We know that IGCT it can block. There are certain types like they can block forward as well as the reverse voltage. If we are having an IGCT that is able to block forward as well as the reverse voltage, that IGCT is known as symmetrical IGCT. This means like this symmetrical IGCT will have the voltage blocking capability on the both sides. Like it will be able to block positive as well as the negative voltage. Now if there is an IGCT that is only able to block positive voltage and is able to conduct this positive current, like that will have a one quadrant operation, like this kind of an IGBT, IGCT is known as asymmetrical IGCT because it is not able to block both positive as well as the negative voltage. Are you getting my point? IGCT having a one quadrant operation like this is an asymmetrical, and IGCT having a two quadrant operation like which is able to block positive as well as this negative voltage is known as symmetrical IGCT. However, for like symmetrical and asymmetrical, they are only able to block voltage in one or both directions, but they are able to conduct the current only in the positive direction. So what we wanted to have, is there an IGCT? We want to have IGCT that is asymmetrical, like that is able to leave asymmetrical aside. We want to have an IGCT that is able to conduct in the reverse direction as well. So what will happen, what we want to do is, at that time what we do is we add this, like this figure where my pointer is right now. We will add an anti-parallel diode across this IGCT. So you can see when the voltage will become negative, like our diode will get forward biased, and it will be able to conduct this reverse current as well, like negative current as well. So for this case, here what will we have? We'll be having a device, IGCT, with an anti-parallel diode with it, which is able to block positive voltage, and which is not able to block negative voltage, but is able to conduct positive as well as negative current. This kind of a device is called an RC IGCT. This means RC is for reverse conducting, like it is able to conduct this reverse current, negative current as well, that will flow through this diode as such. Also it is an asymmetrical because it's able to block only positive only one voltage. It's known as like it is an asymmetrical IGCT. So the answer is asymmetrical IGCT can be found with reverse conducting diode in the same package. So now this is the third, and I think this is one of the important questions, and I think you should be uh, able to guess this right. Like, in case of a high voltage application we use what, and in case of high frequency application we'll be using what. Like, there are certain options and combinations, like for A we are IGBT, and for second also we have an IGBT. And second option is, for first we'll be using MOSFET, like for high voltage application we'll be using MOSFET, and for high frequency or application we'll be using IGBT. Third option is, like for high voltage application we'll be using IGBT, and for high frequency application we'll be using SCR. That's the third option. For fourth option, it is like for high voltage applications we'll be using IGBT, and for high frequency operation will be using MOSFETs. Like you can guess the options of this. Like, I think this is the important question, like you should be knowing for certain applications which of the devices we can use. Any guesses please? Like, some of you have certain guesses, like most of you have guessed it D. Okay, another option for D. Yeah, and someone is saying C. Hmm. So coming out to the solution of this question, we want to see. We want to see the MOSFET structure of this MOSFET and IGBT. Like, as you can see, this figure, is a MOSFET, and this figure has an IGBT. As we had already discussed, like this MOSFET is a majority carrier device, and these majority carrier devices, the conduction helps through these majority carriers. So here, if you can take a look at this structure of the MOSFET, we are having an NPN junction, and we are having a gate. So when we like apply a gate voltage, we want to turn on this MOSFET. We apply a positive gate voltage between gate and source. When the positive voltage is like G is positive, what it will do, like there is a positive voltage between D and S is applied, and when it will attract these negative charges, and some sort of a channel will flow, channel will be formed between the D and S. D and S, and this and because these are the these like N channel will be formed between D and S, and since these MOSFET is a majority carrier device, and that is why this current through this device will be of like when this is in D and S, current will flow, current will be because of the majority carriers, and that are the electrons. Also, like I had previously also discussed, this majority carrier devices, they are operated for higher switching frequencies, because we have not done the conductivity modulation there, like don't have introduced some minority carriers there, which we have to extract at the time of turn off. So in these at the time of turn off, they are able to recover quite fast, and as such, with these MOSFETs will be able to go for higher switching frequencies. But since these MOSFETs, however, these MOSFETs are like lightly doped, we don't have introduced any majority or minority carriers into it. So there is a downside to it, is like we be having a higher on state resistance drop in these MOSFETs. Coming towards the IGBT, let us come towards this IGBT, and this is the structure of this IGBT. And here you can see when this since the gate and is isolated, so when we apply this positive voltage across these terminals, and like this a channel is formed here, but when we apply this, since we have a PN junction here, so when we apply this positive voltage between C and E, like these holes are pushed through the channel, and these electrons are pushed through the channel, which are the minority carriers, which will help in the conduction. So what happens in IGBT is these are like minority carrier device, and we have an extra layer here that's known as drift region, and this drift region because of this drift region will be having the high voltage blocking capabilities, and this more of this drift region, and more will be the voltage blocking capability of an IGBT. Besides this, there are additional like minority carriers introduced into this lightly doped region, and because of that, sorry, just a minute, into this lightly doped region, which helps in the conduction. And since we have introduced these minority carriers into this lightly doped region, this reduces the on state losses, but due to the downside of this is at the time of turn off, we need to extract these minority carriers at the time of the turn off, when the negative voltage is impressed across this gate GE terminal, due to which there will be some negative current, which is on like a tailing current in this IGBT. It will take certain time to come to zero, as such the losses will be more. And if we operate this IGBT at higher frequency, so since there is some current, and there will be some voltage, so the switching losses will be very high, and that we don't want in our practical switch. We want to have as low as losses possible in our devices. So yeah, this means like this IGBT cannot be used, is not feasible. It can be used, but there will be very high losses, and If the losses are very high, like these losses will be dissipated as a heat, and if that will raise temperature of the devices too much, and it can cause damage to the devices as well. So yeah, like these IGBTs are used for high voltage applications, but for lower frequency operations. And for these MOSFETs, they are used for high frequency operations, but lower voltage levels. So the option D is correct. So yeah, I think like we should take a 5 minute break here, and I think we should join at 8:20. Is that fine? Hello?
Okay, sir.
Okay, let us take a 5 minute break, and we'll be joining at around like 5:21 or 5:22. Okay, let us carry on. Everyone is there now? Should we carry on? Okay. Now the question is, another question is like, which of the following characteristics are for an ideal switch? A is on state resistance is 0, off state resistance is infinite. On state resistance is infinite, off state resistance is 0. Third option is on state resistance is 0 and off state resistance is 0. D is on state resistance is 1000 and off state resistance is minus 1000. So like, can you guess the answer? Like, I think all of you should be able to know the answer to this question, because it has been, like, I have also discussed it in detail about this switching characteristic. Anyone else, like one of? So coming to this question, like like I had told in the introduction, for an ideal switch, what we want is, we want to have at the time of conduct, when the switch closes, like V on should be 0. When the switch is conducting, here you can see, when the switch is conducting, V switch is on, like it should conduct infinite amount of current, and that conduction should be in the both directions, like it should be positive direction as well as direct for an ideal switch. That means V on should be 0. This means there shouldn't be any voltage drop across the switch, and that means, like, if there is a current and there is some resistance, on state resistance in the device, there will be some voltage drop. So to have a, in an ideal switch, to have a voltage drop in the on state to be 0, what we need is, it should have a 0 on state resistance. That's for the one, and 0 on state voltage drop. But that is not possible with the practical switch. Like practical switch, there will be some voltage drop, like for a diode it will be like 0.7 volts, and for a Schottky diode it will be 0.3 volts. Similarly, at the time of MOSFET, there will be some RDS on, and the current flowing through this resistance, RMS current will be like the loss, conduction loss through the switch. And at the time of the switch off here, this, when the switch is off, like there should be like no current flowing through the switch, and this means, like uh, the resistance should be the resistance should be infinite, or that high, like it should halt any flow of the current through the device. For practical switch, there is some leakage current that will flow at the time of the turn off. At the time of the turn off, there will be certain current flowing, that is known as reverse leakage current. But for an ideal switch, like no current should flow. There shouldn't flow any current in through the switch. This means, like at the time of the turn off, like the switch off state resistance should be infinite, and there should be like 0 leakage current through this switch. And coming out to be the ideal characteristics of the switch, like this ideal switch should be a 4-quadrant switch, which should be able to like conduct the current in both directions, and should conduct the current infinite amount of the current in the both directions, and should be able to block the voltage, infinite amount of voltage in the both directions. However, that is not possible with the practical switch, where the devices will be able to block a certain amount of voltage for which they are rated, and after that if we impress the voltage higher than that rated voltage, the devices will get damaged. And similar is the case so with the current. If a device is rated for a certain current, and if the current rating of the if the current through the device exceeds that rated current, that then the device will get damaged. So yeah, our ideal switch should have an on-state resistance of a 0 and off-state resistance of infinite, to have to have a 0 voltage drop in case of the on state, and to have a zero leakage current or zero current at the time of the turn off. Now coming to the fifth question. For the regenerative braking, the device which is used is dash: A diode, B triac, C GTO, D both triac and GTO. Anyone? Like some of you have given option A, some of C, some D. So let us go into the question. So first, what do we would understand what we mean by this regenerative braking. So if we can have a like an let us take an example of an electric vehicle where we have a battery pack, then we have a power electronic, like there is a supply, let us say this is a battery pack, then there we have some converter then which drives this motor. So like this motor can have like two modes. It can operate in motoring mode as well as it can operate in the generator mode. What is motoring mode is where the power is power will flow from source to the motor, like it will draw power from the supply so that it is able to drive the vehicle. But there is also a generator mode. In that case what happens is, let us say like our car is going down the hill or there is a braking. At the time of braking or our car going down the hill, there is certain amount of kinetic energy at time of braking associated with the motor, because like our motor is running at a very high speed. So if we brake, there is some certain kinetic energy, we want to dissipate that amount of energy. So one way to dissipate that energy is to dissipate it through some dissipative element like a resistor or so. But what will happen because of what will happen because of that, like the system it will not be that efficient. There is also another way, like if could we use that energy at the time of braking or going down the hill and like feed it back to the source, like for that what we need is like our devices should be able to block the voltage, like it should be able to like carry having the negative, should be able to process a negative power as well. So what should be this the converter, our converter should be should have the characteristic that it should be have the bidirection, it should have the ability of having the bidirectional power flow, like during the motoring mode it should be able to drive the motor. And that means like it should be able that we should be able to supply power from the source to the motor, and during the during the braking we should be able to save this energy and supply this energy back to the source. That's why this means is a regenerative braking. So to meet these conditions, we need to have the switches that are able to have this, that are able to process this negative power as well. Let us first come to this diode. If we see an example of a diode, like some person had thought of an option A. This diode is able to conduct the current in a positive direction only. So it is able to conduct in a positive direction, and it is able to block the negative voltage. So if we see through the current, like the device is able to carry the current in a certain direction, only in one direction. Now let us say like the diode is in the direction of like feeding the power from source to the motor. At the time of braking, like no, the direction of the current will reverse, like it needs to go, like we have to feed power back to the source. So the diode won't be able to conduct that amount won't be able to conduct that the current in that direction. So the first option is not possible. Now coming towards the triac. So what we have with triac is like we can have positive voltage blocking as well as negative voltage blocking. It is able to block the positive voltage till the certain gate current is given. And with the the triac are like two anti-parallel, like triac is like two SCRs connected in the anti-parallel fashion with a common gate. So this triac is able to block both positive as well as the negative voltage, and is able to conduct the current is in both directions, like positive and negative. So at the time of regenerative braking, so when there is a reversal of the current, so now the direction of the current is towards the source, so that reverse current can flow through the triac. That means like if we are having these devices in our power converters, like they will be able to process this negative power. So this one option is correct. Now we'll see with GTO. So with GTO, like there are certain cases where the direction of the current doesn't change, but there is a reversal of this voltage, and we know like this GTO is able to block positive as well as negative voltage, but is only able to conduct the current in the positive direction. So there are some cases where it can process this negative power, like power that can be fed back to the source. So this GTO also has the capability of processing this negative power or reversal of power. As such, this can also be implemented for this regenerative braking. So the option D is correct for this. So now coming towards this sixth question. How to turn off the GTO? First option is A, by applying a high negative gate current at the gate. B is by applying an anti-parallel diode with the device. C is by applying a freewheeling diode across GTO, and D is none of these. I want to guess. One of the person is saying like D, and most of you are saying A. Let us go to the circuitry. Like towards my left is an SCR circuit, and towards my right is a GTO. So we know like a GTO is an improvement. I had previously also talked about it. Like a GTO is an improvement over an SCR. So towards the left uh, is an SCR. So we know like these are the current fed. These are the current fed devices. So when a gate current, when a positive gate current is given, like and there is a positive voltage between anode and cathode, like J1 and J3 are forward biased, and J2 is reverse biased. And when the positive current is when the gate voltage gate current exceeds the threshold, channel is formed, like, and SCR starts to conduct. However, when we give the negative, when we give this negative this current through the gate, what happens is only G3 is reverse biased, and this J1 will remain forward biased, and it won't like turn off. However, as compared to this SCR for the GTO, the structure of GTO is in such a way, like for the turn on, we know when we provide a positive gate current, J1 and J3 are forward biased, and J2 with the gate current above the threshold, it is able to conduct. It is able to conduct. However, when we apply the negative current through this gate, the entire PN junction get reverse bias when we apply this negative current through in GTO. The circuitry is shown, and which you can see in the detail. So the answer to this question is by applying a high negative current at the gate, GTO can be turned off. Moving towards the seventh question. The switching times of a MOSFET essentially depends on, the first option is frequency of the supply system, B is the charging and discharging rate of the parasitic capacitors, C is the charging and discharging rate of parasitic inductors, D is power voltage current of the given system. Can anyone guess the answer? Like one of you have written the option B. So anyone other? Any other? Okay, like most of you are telling it is a B option, and someone is saying C. Let us go deep into it. So the figure shown here, is how we can model a MOSFET. So MOSFET like has a three terminals: gate terminal, drain terminal, and source terminal. And between these terminals there is some parasitic capacitance between these terminals, like between gate and source there is some capacitance which we call like gate source capacitance, and similar to this gate source there is a capacitance between gate and drain, and that is called a gate drain capacitance. And between drain and source there is a parasitic capacitance known as the drain source capacitance. So this is how we model, this is how a MOSFET is modeled. So we know, like for the MOSFET is a like voltage control device, and the current through the drain to source is a function of this gate source voltage. The rate at which this drain current change will depend upon the rate at which this GCS is charged. So what we want is, like for a MOSFET, let us say 15 volt is a turn on. So what we will give, we will be giving that voltage across this GS. However, that GS, since GS is across that voltage, that full 15 volt won't get impressed across this gate source terminal, as we had already seen that capacitor will resist the change in the voltage, won't allow like a very won't allow the instantaneous change in the voltage. When the voltage applied, like there will be certain rate of change of voltage, and then this capacitor will be charged to a certain voltage, and our gate source will turn on. So how fast will this GS capacitance turn on will be charged, will determine our turn on of this device. So if this capacitance is very small, and this capacitor is charged very fast, like we can have a faster turn on. So if this capacitor value is large, we can then it will take some time to charge this capacitance, and our turn on time will be large, like it will take certain time to turn on. And at the time of, like when the device will turn on, before the turn off of this device, there will be some voltage which will be blocked by with this drain source terminal. So there will be some charge across this VDS and VGD that needs to so these before, like turning on the device, these capacitors need to discharge so that the voltage will come to be zero, and our MOSFET will start conducting. So, and the values of like these capacitance are given uh, data sheet of the certain of a certain switch. I can take it a IGBT or a MOSFET. The values are given there by the manufacturer. So yeah, for this turn on of the device, what we require is, like in turn on of the MOSFET will depend upon at which rate GS is getting charged, and this DS is getting discharged. And these on the data sheets, what is given is like CISS and COSS voltage, which is equal to like CGD plus CGS. Like, I don't want to go into the detail as of now, like which you will subsequently learn in the course. And this is how, like these capacitances, like we are given this CISS, USS, CRSS voltage. So from that we can determine these voltages. Yeah. So this so the answer to this question is the charging and discharging rate of these parasitic capacitors will determine the switching of our, like turn on and turn on of our MOSFETs, how fast our MOSFET will turn on or turn off. So, yeah. Moving to the next question, which of the following relation is true? Like I don't want to guess it here, like this is some my mathematical problem. So we'll be discussing what is a form factor and what is a ripple factor first. So as you have seen in the later part of your course, this what was taught in this week in the like single phase AC/DC converters, there are certain factors which determine our which determine our waveform shapes, how close it is to the sine wave, and all. And one such factor is like form factor. Form factor is given by this equation, which is the ratio of this RMS to the average value. As you can see, form factor is a ratio of the RMS to the average value. If we have a DC, if we have a pure DC, we have a like RMS and average value are same. Therefore, we have a form factor of 1. Now, if we have a pure AC, we have average value of 0. This means that we have an infinite form factor. And there is also a ripple factor which is given by this equation, like this is the root of the RMS value of RMS value minus average value divided by the average value, which can be rewritten in this way, like ripple factor will be given the root of form factor square minus 1. This means if we have a pure DC, I had told you, like for pure DC form factor is 1, that means our ripple factor is 0, like there will be no ripple in the pure DC. Now what is given in the question is, like if we have a form factor of root 5, what is the ripple factor? So can anyone do the calculation and tell me which of the answer is correct? Like the formula is here. Anyone? Okay. No one. So given this formula, if we take the first form factor is root 5. If we take a form factor of root 5 square, root 5 square will be 5, 5 minus 1 will be equal to 4. So if we have a form factor of root 5, we can get a ripple factor of 2. That means the first one is correct. Like you can check it for other as well. Like what we get is, like first option is correct. Like this is a numerical problem. Like you have to put the value and calculate it. Like this is not some very high-fi numerical, like this is some basic numerical, like use the formula and get the answer type numerical. So there's another question. In IGBT, the P plus layer connected to the collector terminal is called as A, drift layer, B, injection layer, D, C, body layer, D, collector layer. Can anyone answer the question? One of you has said B. Can anyone else? Another is D, B. Okay, let us go towards it. Like we will see this IGBT structure. We know in case of MOSFET and IGBT, whenever we apply a certain gate, there is a channel is being formed, and through that channel the conduction happens. Like in case of IGBT, in case of an IGBT, it is through minority carriers. In case of a MOSFET, it is conduction is through majority carriers. Like this, if you can see this picture, like this is the NP. This is this now IGBT structure, and this can be shown here in another way. Like we have in towards the collector we have a P, then we have a heavily doped N region, lightly doped N region, and then we have towards the gate we have a PN junctions. So this lightly doped region is called a drift region, and plus called a buffer layer, and the P layer that is close to the collector is called injection layer. Why it's called an injection layer? Like when we apply a positive charge towards the P, like it will repel some holes, and those minority carriers will get injected into the N layer. So what happens with the application, like this layer injects more minority charge carriers into the N layer across this PN junction diode. That is why this layer is called an injection layer. So option B is correct. Like this is known as the injection layer. Coming towards the last question. In a certain power electronics application, it is required that the voltage at the load terminals is to be kept within a certain range of voltages only. Among the devices listed below, which would be the most ideal choice for this application? A is PN junction diode, B is Schottky diode, C is Zener diode, D is fast recovery diode. I think this isn't being taught to you, but if anyone could guess, what should be the answer for it? So most of you have said like Zener diode, like maybe you would have read it in like 11th, 12th. You can see Zener. This is the characteristics of a Zener diode. And about the Zener diode, like Zener diode is like PN junction diode, which is heavily doped. Due to the heavily doping of this Zener diode, when it's reverse biased, a small depletion region is formed. When the reverse voltage is applied across this Zener diode, a small depletion region is formed, and as this will be able, because of the highly doped, there are large carriers present in this Zener diode, and when the voltage exceeds the threshold breakdown voltage, what happens? There is an avalanche breakdown. Avalanche breakdown, this means like a current will increase rapidly, and voltage will drop to like voltage will drop. So what we can see, like when at the time of this breakdown, when there is an avalanche of breakdown like this, at the this knee, towards this knee point, this Zener diode is able to withstand that amount of voltage, and after that what happens is there is an avalanche of current and avalanche of current. So up to that portion, because of this heavily doping and heavily charged carriers, it's able to block a certain voltage, and as such you would have seen in certain applications, so to regulate the output voltage, like we'll be using the Zener diode, so that it will block voltage up to certain point, and after that when the voltage exceeds that point, there is a breakdown and a huge current will flow due to the abundance of charged carriers, yeah. And yeah, and as such, like this Zener diode is being used for the voltage regulation purposes. So the answer is Zener diode. And yeah, that is what was for today. Like these are the questions, uh, uh, these were the questions that were for today, and maybe like your deadline for this these assignments is 9. Maybe from the next in the next problem solving session we can see this the next problem solving session next problem solving session, we can solve these assignments as well, and subsequent classes will be having, will be problems will be more of a numerical, more into the numerical part, because now we are moving towards this AC/DC converters, and some of the problems will be numerical. Also we'll be solving these assignments, as well as there will be certain problems with regards to the what will be taught in the coming week. So yeah, anyone having any question, like he or she can ask. Like there are still a few minutes, and if there are no questions, then we can close the session. Vishwanathan Murli has raised a hand, and
So, sir, the reverse current required to break conduction for SCR and GTO. GTO is greater. Why, sir?
what I'm not able to.
Reverse required charge is greater for GTO because higher current is required for breakdown. Reverse current. Why, sir?
So Reverse recovery time of this GTO will be higher because if I'm able to understand your question is we in the GTO is an improvement over a SCR. We had taught like the improvement is in terms of that SCR has a high on state these on state resistance. So we want to decrease that on state resistance. So what we are introducing some because these are the minority charge carriers, we do the conducting modulation. We have introduced some this minority carriers in this lightly doped region, which will decrease this RDS on. But at the time of turn off, what needs to be done is like we have to extract these minority carriers as well. So because of that, it will take certain like more amount of time, more time to turn off this device than GTO.
Okay, sir.
Any other question? Okay, if there is no question, then we can close for today.
Sir, holding current level, which one is higher, sir?
Yeah, what?
Holding current. GTO or SCR?
Holding current. Okay.
Yes, sir.
Okay, for that, like you have to see the characteristic equation, like in a characteristic graph of this GTO. Because like since that is what I was telling you, like there are like we have introduced more minority carriers. I think this is the answer to it, and if not, I'll still check it and we'll come back to you, because we have introduced more minority carriers. It will require like a more amount of current to withstand up to that holding current value, and maybe
Sir,
yeah.
but there is reverse recovery charges, sir. That will influence on holding current, sir.
Yeah, and I think for no, reverse recovering is not a holding current is the amount of the current in the SCR above which, like if we will turn on the device, it won't turn on off, like it will start the conducting. If you can see that graph of the SCR VI characteristic, that is the holding current.
Thank you. Okay, sir. Thank you.
Any other question? If
Thank you so much, sir.
okay, thank you everyone. Okay, so we can close this for today.
Hello.
Yes, sir.
Hello.
Yes.
Hello.
Yes.
Sir, is audible?
Yeah, you are audible. Yes.
Yeah, in controllers, EV controller, while we riding with sources, it act like a motor. While applying the brake, it produces a regeneration.
Yeah.
In controller side, they have only a MOSFETs. But how it's reversing the current?
So what happens with the MOSFET? Like it has to conduct the. If we can see the packages that MOSFET come in, they don't come as a MOSFET only. They have an anti-parallel diode connected across the MOSFET. So when there is a reverse current that flows through that diode, anti-parallel diode.
For only reversing the diode is used.
Yeah, to have this, like so that it can have this negative current can flow through it. We had also seen in the characteristic, if you can go back towards the previous class, like MOSFET was able to conduct with an anti-parallel diode, was able to conduct in both directions, like positive as well as negative. Like you'll see like MOSFET will operate in this first and fourth quadrant.
Okay, sir.
Go through that.
Okay, thank you, sir.
Okay, that's for today. So we'll be closing towards session. Good night, everyone.